For as long as humans have gazed at the night sky, comets have captured our imagination. These celestial wanderers blaze across the heavens, their luminous tails trailing behind only to vanish into the darkness. Ancient cultures saw them as omens, mysterious messengers from the gods, inspiring awe and fear. Today we see comets as cosmic visitors, their rare appearances reminding us of the vast, ever-changing universe. Unlike the steady stars or familiar planets, a comet's arrival is a fleeting spectacle, a reminder of our place in the cosmos. Comets journey from the coldest reaches of the solar system, made of ice, dust and rock. As they near the sun, their ice vaporizes, creating a glowing coma and a tail that can stretch millions of kilometers. This transformation, from frozen relic to radiant beacon, is a cosmic display of physics and chemistry. Each comet is unique, a time capsule carrying the primordial materials from which our solar system was born. Our fascination with comets has evolved from superstition to scientific curiosity. No longer omens, they are now windows into the past, offering clues about the origins of our cosmic neighborhood. Comets challenge us to understand where we came from and how our solar system formed. The quest to unlock their secrets is a journey from ancient myth to the frontiers of space exploration. They are not just beautiful, they are profoundly important. In studying comets, we seek to understand ourselves and our place in the universe. The allure of comets endures, driving us to explore the mysteries they hold. Comets have always posed more questions than answers. What exactly are they made of? Is it just water ice, or do they contain other frozen compounds and mysterious dust? Are they solid and dense, or fragile and fluffy? Their structure determines how they behave near the sun and how they evolve over time. Beneath their weathered crusts, could there be untouched material from the dawn of the solar system? And did comets deliver water and organic molecules to early Earth, seeding the ingredients for life? To solve these mysteries, we needed to get closer, much closer. We needed to look inside. To truly understand comets, NASA devised a bold plan: hit one with a spacecraft. Telescopes could only study the surface, but to reveal a comet's secrets, we needed to excavate. The Deep Impact mission was born, its goal to crash a probe into a comet's nucleus and study the resulting plume. The target comet Tempel 1, a reliable short-period comet about 6 kilometers across. The mission was a high-stakes gamble, requiring precision navigation to hit a small, fast-moving target millions of kilometers away. The plan sent a spacecraft to release an impactor, which would collide with the comet, blasting material from deep within. Instruments on the main spacecraft and telescopes worldwide would analyze the ejected material. This was more than a flyby. It was an experiment on a cosmic scale. For the first time, we would actively probe a comet's interior, not just observe from afar. The mission captured the spirit of exploration, pushing the boundaries of what was possible. Success would mean a new era in understanding the building blocks of our solar system. The world watched as NASA prepared for this unprecedented encounter. The stage was set for a collision that would change our view of comets forever. Deep Impact was about to make history. The countdown to impact had begun. Deep Impact was actually two spacecraft in one, the Flyby and the Impactor. The Flyby was the mission's observatory, equipped with cameras and spectrometers to capture every detail of the impact. Its job: deliver the Impactor, then retreat to a safe distance to record the event. The Impactor, a 370-kilogram copper projectile, was designed to avoid contaminating the scientific readings. It wasn't just a dumb bomb. It had its own camera and navigation system to steer itself into the comet. Launched in January 2005, the spacecraft traveled over 430 million kilometers, guided by careful navigation and course corrections. As they neared Tempel 1, tension mounted. On July 3, 2005, the Flyby released the Impactor on its final one-way journey. The two crafts parted ways, the Impactor locked onto its target while the Flyby moved to a safe vantage point. The mission was a testament to human ingenuity and precise engineering. Everything was ready for the cosmic experiment to begin. The world held its breath. Deep Impact's voyage was a silent trek across the solar system. For 172 days, the spacecraft cruised toward its rendezvous with Tempel 1. Mission teams monitored its health, refined its trajectory, and prepared for the encounter. As the comet grew from a faint point to a detailed object, The flyby's cameras captured invaluable images. The final 24 hours were a test of autonomous navigation. After separation, the impactor's autonav system took over, guiding it towards a well-lit target on the comet's surface. Tiny thruster adjustments ensured pinpoint accuracy. This was a triumph of technology, guiding a probe to strike a moving target millions of kilometers away. Months of travel would culminate in a split-second impact. The universe was about to witness a human-made collision. July 4th, 2005, Independence Day. The world watched as the impactor raced toward Temple 1 at 37,000 kilometers per hour. In NASA's control room, anticipation was electric. The impactor sent back images until its final moment. Then silence. Success! The probe had struck its target. The flyby spacecraft, 500 kilometers away, recorded a brilliant flash and a spectacular plume of ejected material. The impact was more dramatic than expected, equivalent to 5 tons of TNT. Observatories worldwide, including Hubble and Spitzer, captured the event in multiple wavelengths. It became one of the most observed astronomical events in history. The public was captivated, sharing in the wonder of discovery. Data streamed back high-resolution images and spectra revealing the evolving plume. The experiment had worked. The secrets of Temple 1 were now exposed. For a moment, the world united in awe at a human-made event on a distant comet. The era of passive observation was over. We had become active explorers. The impact marked a turning point in comet science. The real discoveries were just beginning. The moments after impact were a frenzy of data collection. The flyby had just 13 minutes to capture the evolving plume before moving to safety. Its instruments worked flawlessly, recording the expanding cone of dust and ice. Telescopes on Earth and in orbit joined in, providing a multi-wavelength view. The plume was brighter and denser than expected, revealing Temple 1's nucleus was porous and fragile, more like powdered snow than solid ice. The impactor buried itself deep, ejecting a huge volume of material. Scientists watched a crater form in real time, estimating it to be about 100 meters wide. Every observation brought new insights into the comet's structure and behavior. The true treasure was in the light from the ejected material. Spectrometers revealed water ice, confirming the dirty snowball model, but there was more. Frozen carbon dioxide and complex organic molecules, including precursors to amino acids. This supported the idea that comets could have delivered life's building blocks to early Earth. Fine silicate dust suggested Temple 1 was layered, not uniform, evidence of a complex formation history. Surprisingly, the interior material resembled the surface, hinting at internal mixing over billions of years. Comets, it turned out, were not simple relics but dynamic, evolving worlds. Deep impact revealed a heart far more complex than anyone expected. The findings reshaped our understanding of how comets and perhaps life itself came to be. The mission's discoveries would echo for years. Deep impact changed everything. It proved comets are complex, layered, and surprisingly fragile. The mission's success inspired new missions to land on and sample distant worlds. Discoveries of water and organics supported the idea that comets seeded Earth with life's ingredients. The flyby craft's extended mission to Comet Hartley 2 revealed even more diversity among comets. Deep Impact was more than a science mission. It was an inspiration showing what's possible when we dare to explore. Sometimes, to understand the universe, you have to make an impact. The quest to unravel our cosmic origins continues, driven by curiosity and the enduring allure of comets.